In this video, we will look at the second scenario where the ball is thrown vertically upwards, reaches the highest point, momentarily at rest, and then it comes back to your hand. As the ball is being thrown upwards, we will fix up as positive, so the beginning part we will draw on the positive section of the graph. As the ball leaves your hand, the speed is the maximum, and as it goes up, the speed decreases until it reaches the highest point where momentary is at rest. Let's call this point A here, this is point B. So let's start with point A. Now, point A will not start from the origin because, as mentioned, the moment the ball leaves your hand, it is the maximum speed. Another way of thinking is, how do you know? Because as it goes up and until the highest point is at rest. So that means to say the speed must be decreasing. So in other words, at point A, at time equals to 0, the velocity will be the maximum. Let's put an imaginary number. Let's say it's 20 meter per second. We're going to assume the case where there's no air resistance. So let's draw the free body diagram when the ball is going up. So it's going upwards, and the only force that's acting on the ball is its weight. So your F net is equals to minus weight. Why minus? Because the weight, the net force, is opposite to the motion. So your MA equals to your minus mg. Your acceleration will be a negative 10 meter per second square. In other words, it's decelerating, constant deceleration. And let's proceed to the graph. A constant deceleration will be a straight diagonal line with constant gradient until it reaches the highest point. This corresponds to your point B, where it reaches here, the speed will be 0. And this is your point A, the moment it leaves your hand with the maximum speed. And you should know that the area underneath the graph over here, let it be h1, that will be the maximum height from A to B. Next, let's consider at the highest point, point B, where it's momentary at rest. Now, the acceleration is not 0 because if you look at it, at the highest point, the only force acting is your weight. So F net is equals to your weight, ma equals to your mg, so your acceleration will be your 10 meter per second square, just like your gravitational field strength. So even though at the highest point is momentary at rest, making a U-turn, there is acceleration due to gravity and is always downward. And the magnitude is 10 meter per second square. That's why at the speed equals to 0 here, there is a gradient, which is 10 meter per second square. Next, let's consider the motion where it's coming down, and you should know that the speed is increasing until just before it reaches your hand. That's the maximum speed, and then when it reaches your hand, it will come to a complete stop. So let's consider as it's moving down, the only force acting is downwards and the ball is going down. So your F net is equals to your weight, and ma equals to your mg. So your acceleration will be a constant 10 meter per second square. So it will just continue with the same gradient until, if here is 20, when it leaves your hand and just before it reaches your hand, the speed will be the same magnitude, but it will be negative 20. The negative sign because of the direction is opposite. And lastly, when it reaches your hand, it will go to just an instant, come to a rest. So this is your point C just before it reaches your hand. And for the area underneath the graph here, let it be h2, and this the path that the height that it comes down here is h2 and is equals to your h1. In other words, the area here will be identical to the area here. Next, we're going to consider the scenario when there's air resistance. As mentioned, you can treat it as the ball is very light, so the air resistance will be present. And same thing at point A here, when you threw the ball up, let's assume the speed is the same, so this point will be identical. And as the ball is going up, you know that the speed decreases, but the deceleration will no longer be constant. And let's draw the free body diagram. If the ball is going upwards, besides the weight that's acting downwards, there will be air resistance acting downwards, also opposing the motion. So your F net right now will be negative the sum of your weight plus your air resistance. Now, as mentioned, as the ball is going up, the speed is decreasing, your air resistance will be decreasing. So weight being constant plus the air resistance, which is getting smaller and smaller, the overall magnitude, the net force will get smaller and smaller. So your net force equals to minus ma. So since your net force is decreasing, your negative acceleration will be decreasing. In other words, it will be a decreasing deceleration. And how do you draw that on the velocity time curve? So the graph will not be a straight line, it will be curved. It will curve this way, then somewhere around here. Now at this point you might wonder, why do I curve it this way? It's steeper than the 10 meter per second square. Why is it not more gradual, or rather why is it not curved this way? As mentioned first, since the deceleration is decreasing, so the gradient should get less and less steep. So now about the point where why is it steeper, why not the other this way, is because, can you see the magnitude? Previously, the magnitude of the net force is only the weight, but now the magnitude is actually greater because beside the weight, you are going to add in your air resistance. So the overall net force will be greater than just now. So the overall deceleration will be greater than just now. That explains why it is steeper, meaning greater deceleration to start with. So as it goes up, the speed decreases until this point. This will correspond to your point B, and the point B will not be at the original height of the red color. It will be somewhere around here. Because of your air resistance, you will never reach the original height. So you reach somewhere around here and let it be H3 here. And you should know that the area underneath the graph over here, that will be your H3. Another thing to take note of is the gradient at this point where it hits the horizontal axis. The gradient must be equals to the gradient of the red color. And why is it so? It's the same thing. At the highest point, there's no air resistance because the ball is not moving momentarily at rest. So the only force acting is your weight, and the acceleration is basically 10 meter per second square downwards. So that means since the gradient of a velocity time curve is the acceleration and both are 10, so you have to make sure that the tangent here is equals to the gradient of this straight line over here. So this is one thing you need to take note. Next, as the ball is coming down, all right, let's draw the free body diagram. So the ball is going down, the weight is down, and the air resistance is against the motion, so it's upwards. So if I were to do my net force, that will be your weight minus air resistance. Then as mentioned, as the ball is coming down, the speed increases and your air resistance will be greater. So if your air resistance is greater, your weight being constant, weight minus air resistance, this is going to make the net force, which is equal to ma, to be getting smaller and smaller, and therefore your acceleration downwards will be decreasing. So how do you draw that on the graph? So from here, the highest point, you will just draw a decreasing gradient, getting less and less steep, and then when it reaches your hand, it will come to a complete stop. That will correspond to your point C over here. Now you might be wondering, should the point C here be at the timing before the red color or after? Actually, I'm not so sure also, but I believe there are a lot of parameters that affect that. And for our level, actually, we should not be concerned with that. If they want us to plot accurately, most probably they will give us the timing or even the speed when just before it reaches the hand. So for our level, we are more concerned with the general shape. Like I say already, it should be steeper. And then this gradient here, you have to pay attention, make sure the gradient is the same. And then it comes to, it's getting less and less steep over here. So as it falls, it might even reach terminal velocity. So it might be a horizontal line here. So there are possibility for that. So lastly, let's look at the area underneath the graph here. That let's give it H4. So H4 is over here. And of course, it's not drawn to scale. You should know that the area here must be equals to the area here because H3 and H4, they are the same height. And of course, they will not, for our level, they will not ask you to find the area because it's a curve. We are not going to use integration for that. One thing that I missed out just now was when there's no air resistance, this timing you should know that is 2 because the deceleration here will be 10 meter per second square as mentioned. So that means to say every second the speed will decrease by 10 meter per second. So starting from 20, 1 second later it will become 10, and then 2 seconds later you'll come to a rest at point B. As for where's the B for when there's air resistance, this one we will not know the exact value unless they give it to us, but we know that it will be less than 2 seconds. So I hope with this video you are more confident in sketching out the velocity time curve for the two scenarios. All right, thank you.